Here's something that will mess with your head. Watch this clip and try to pinpoint the exact moment it stops feeling like a robot. That uneasy feeling you just got? Scientists have a name for it, the Uncanny Valley, a psychological no man's land where something looks almost human, but your brain can't fully accept it. For decades, robots lived deep in that valley. Stiff, mechanical, obviously fake, but a robot just walked out of Shanghai that sits right on the edge of something none of us have seen before, and nobody's quite sure how to feel about it. This is Moya, and today we're breaking down exactly what makes it the most socially convincing humanoid ever shown to the public, and what it tells us about where this technology is actually heading. DroidUp, a Shanghai-based robotics startup, just unveiled what they're calling the world's first fully biomimetic embodied intelligent robot. Strip the jargon, and here's what that actually means. They didn't build a machine that can walk. They engineered something that exists in the world the way a person does. Physically, socially, and emotionally. And the details of how they pulled that off are worth going through one by one. Start with micro-expressions. This is the detail that separates Moya from almost everything else out there. Human faces communicate constantly, even when we're not trying. Tiny muscle movements around your eyes, cheeks, and mouth shift in milliseconds, and your brain reads them almost subconsciously. Most humanoids completely fail here. They can smile, they can blink, but the timing is wrong. The transitions feel mechanical, and your brain immediately flags something as off. DroidUp says Moya can reproduce those micro-expressions, not just preset poses, but the subtle, dynamic shifts in between that make interactions feel genuine. If that holds up at scale, it's one of the most significant leaps in social robotics we've seen. Then there's something almost nobody else is talking about: body temperature. Moya maintains a surface temperature between 32 and 36 degrees Celsius, exactly in the range of human skin. That might sound like a minor engineering footnote, but think about what it means in practice. Human perception is multisensory. Cold metal or plastic breaks the illusion the instant you get close. A robot that feels warm to the touch engages a completely different part of your brain, the part that responds to other people, not machines. For healthcare applications, elder care, or any kind of long-term human-robot interaction, that single detail could change how acceptable these systems are to the people who actually have to live alongside them. On the movement side, DroidUp claims Moya's gait achieves 92% accuracy compared to human walking patterns. That number matters because most humanoids are optimized purely for stability, staying upright, not falling over. What they sacrifice is naturalism. Human walking is actually a controlled fall, a fluid and slightly asymmetric process of constant micro-corrections. When your brain sees something walking with perfect mechanical symmetry and zero variation, it reads it as wrong before you can even put words to it. Moya appears to be solving that problem in a way other systems haven't managed. Physically, the design is equally intentional. At 1.65 meters tall and roughly 32 kilograms, Moya sits at average adult human scale, but weighs surprisingly little for a full humanoid, suggesting lightweight internal materials and a frame engineered to keep mass down without sacrificing smooth motion. The outer design uses a modular approach, meaning the face and surface layer can be swapped without rebuilding the mechanical platform underneath. That's a smart commercial decision. A hospital might want one aesthetic, a luxury hotel wants something entirely different. Same robot, different presentation. There are unconfirmed reports from robotic publications that Moya is built on something called the Walker 3 chassis, a name associated with UB Tech, one of China's most established humanoid robotics firms. Neither DroidUp nor UB Tech has confirmed any connection, but if platform sharing is happening behind the scenes, it would explain how a newer company is fielding hardware this polished, this quickly. Either way, DroidUp hasn't released a full hardware breakdown, which has only added to the speculation. Moya is expected to enter the market by late 2026 with a starting price around 1.2 million Japanese yen. That positions it clearly as a premium institutional product, healthcare facilities, high-end hospitality, education, not a consumer gadget. And when Chinese social media got its first look, the reaction was almost perfectly split. Half the comments said this is the future of companions and service robots. The other half said it gave them chills. That tension isn't a flaw in Moya's design. It might actually be proof that it's working. While Moya is engineered for the warmth of human spaces, another Chinese humanoid was busy proving it could survive somewhere most electronics simply quit. Unitree Robotics recently sent its G1 humanoid on a fully autonomous trek across a snowfield in Xinjiang's Altai region at minus 47.4 degrees Celsius. That's minus 53 Fahrenheit. The kind of cold that cracks metal, thickens lubricants into paste, makes plastics brittle, and kills battery cells in minutes. The G1 didn't just survive, it walked more than 130,000 steps while tracing a precise path in the shape of a Winter Olympics emblem. 186 meters long, 100 meters wide, across uneven, icy terrain. Think about what that actually requires. It's not a straight-line endurance test. It's centimeter-level positional accuracy, maintained continuously using China's Beidou satellite navigation system. It's adaptive path planning algorithms making real-time corrections as the surface shifts beneath it. And it's stable bipedal locomotion the entire time, which is genuinely difficult in a climate-controlled lab, let alone in conditions that brutal. To handle the cold, engineers made some pragmatic field modifications: an insulated puffer jacket over the torso, improvised plastic covers on the lower limbs to protect joints and actuators from freezing. It's a reminder that even cutting-edge robotics sometimes needs low-tech solutions. The G1 stands 127 centimeters tall, weighs about 35 kilograms, and runs between 23 and 43 joint motors depending on configuration, with a maximum joint torque of 120 Newton meters. A 9,000 mAh quick-release battery gives it up to 2 hours of operation with fast swap capability in the field, and an 8-core processor handles all joint control at walking speeds up to about 4.5 miles per hour. The AI system powering it, Unitree's UniFo-LM, uses reinforcement learning for motion control and task execution. Originally introduced in May 2024 as Unitree's entry-level humanoid, the G1 starts at around $14,240 and Unitree reportedly shipped more than 5,500 humanoid robots in 2025 alone. That last number is worth sitting with. This isn't prototype territory anymore. This is manufacturing scale. And the fact that their entry-level unit is trekking autonomously through conditions that would end most consumer electronics says something significant about where the reliability curve is heading. From extreme cold endurance to a very public stumble in a shopping mall, Chinese EV maker Xpeng brought its Iron humanoid to a live consumer demo ahead of a planned 2026 mass rollout, and the first half of the event was genuinely impressive. Iron walked a choreographed catwalk, interacted with spectators, and stood on stage next to a child in a way that read as approachable and natural. Then, while standing still, it lost its balance, tipped backward, and fell face down on the stage. A staff member partially caught it. The robot was quickly removed, adjusted, and brought back. But for the rest of that day, it stayed strapped to a support frame, limited to educational interactions only. The fall became a trending topic across Chinese platforms almost immediately. But here's the context most of the coverage missed. Bipedal balance is one of the genuinely hard problems in robotics. Humans maintain balance through thousands of micro-corrections per second, drawing on the vestibular system, visual input, proprioception, and years of embodied muscle memory. Replicating that in a machine, especially while standing still, where you lose the stabilizing momentum of motion, is extraordinarily difficult. The fact that Iron had multiple flawless demos before this moment matters. One fall doesn't erase real engineering progress, but it does show, with unusual clarity, exactly how much margin still exists between an impressive demo and a system you can trust in the field. The engineering inside Iron is genuinely sophisticated. It stands 178 centimeters tall, full adult human scale, weighs 70 kilograms, and has 62 active joints, including hands with 22 degrees of freedom each, capable of handling both delicate and bulky objects. A curved wraparound display serves as its face, dynamically shifting expressions as it speaks. Processing is handled by 3 Turing AI chips, delivering a combined 2,250 trillion operations per second. Power comes from an all-solid-state battery, chosen for both extended runtime and improved safety. The robot can walk at up to 2 meters per second and was trained on thousands of hours of human motion data through Xpeng's Vision Language Action System, which links perception directly to physical movement. Structurally, Iron is built around a 5-degree of freedom spine, unlike most humanoids, which treat the torso as a rigid block. The hip structure is designed for fluid, dynamic balance. A 3D printed lattice fascia layer underneath the outer suit mimics human musculature, dampening the micro-vibrations that give robotic motion its characteristic jerkiness. On paper, it's one of the most thoughtfully engineered humanoid platforms announced anywhere in the world. The challenge, as that fall illustrated, is the gap between processing power and real-world physical reliability. That gap is where the entire industry is currently at war with itself. While companies race to ship humanoids, researchers at Harvard School of Engineering are attacking the fundamental physics of robotic movement. And they may have quietly cracked something important. The team developed a new robotic joint design inspired by the human knee, built around what are called rolling contact joints. Instead of a fixed pivot point, which is how the vast majority of robotic joints work, these use pairs of curved surfaces that roll and slide against each other, connected by flexible elements. The geometry of the contact surfaces isn't arbitrary. The team created a mathematical method to optimize those exact shapes based on the specific forces the joint will need to handle. The joint itself is engineered for its task, not just a generic hinge doing its best under load. In testing, the results were dramatic. A knee-like joint built this way corrected misalignment 99% better than a conventional design. A two-finger robotic gripper using the same approach held more than 3 times the weight of a standard gripper, using the exact same actuator and the exact same power input. Read that again. Same motor, same energy, 3 times the useful output. In robotics, that is not a minor optimization. It potentially changes what's achievable at a given weight class and power budget. The applications reach from exoskeletons and prosthetics to humanoid robots and biomechanical research into how animals move. But for humanoids specifically, this is the kind of foundational work that could quietly redefine what joints cost, how much they weigh, and how reliably they perform. Not next year, but across the next decade. There's a limitation most humanoid robots share that you've probably never consciously noticed, because it only becomes obvious once someone points it out. Watch almost any humanoid manipulation demo carefully and you'll see it. The robot walks to a position, plants its feet, stabilizes, and then it picks something up. Motion and manipulation are treated as 2 separate modes, not one continuous action. That's not how humans work, and it creates a ceiling on what humanoids can actually be useful for in real environments. Westwood Robotics is directly challenging that ceiling. Their Themis Gen 2.5 runs on what they call an AI-augmented humanoid operating system, a tightly integrated architecture where perception, planning, and motor control all run simultaneously rather than in sequence. The practical goal is a robot that can carry objects, manipulate its environment, and navigate all at once, the way a person does when they're carrying groceries while opening a door. Their whole-body loco manipulation controller uses sensor fusion and real-time state estimation to maintain balance while the arms are actively working. A multi-layer mapping system with semantic understanding lets it plan paths while recognizing what it's looking at. The vision system with what they call OCVAM, an object-centric vision action model, links visual perception directly to physical action without burning excessive compute in the process. The hardware received serious upgrades alongside the software. Each arm now has 7 degrees of freedom and can handle payloads of more than 5 kilograms. New actuators in the hips deliver over 120% more torque while generating roughly 80% less heat. That heat figure deserves attention. Thermal management is a quiet bottleneck in robotics. Actuators that run hot throttle their own performance, reduce their lifespan, and create safety concerns the moment a robot is operating near people. Cutting heat output by 80% while simultaneously increasing torque by 120% is the kind of engineering compound win that changes the economics and safety profile of everything else the robot does. Step back and look at everything we covered today. Not as isolated stories, but as a pattern. Because there is one, and it's moving faster than most people realize. Moya is showing that human comfort and social acceptance might matter more than raw capability in the robots most likely to enter daily life. Not the most powerful robot, not the most technically impressive, the one that feels most familiar. That's a design philosophy shift with enormous commercial implications. The robots that win in homes, hospitals, and service industries won't necessarily be the ones that can do the most. They'll be the ones people don't instinctively pull away from. The Unitree G1's Xinjiang trek is proof that reliability at scale is no longer theoretical. More than 5,500 units shipped. Minus 47 degrees. 130,000 steps across terrain most humans would struggle to walk. The gap between lab demonstration and operational deployment is closing faster than the industry's public narrative tends to acknowledge. Xpeng's Iron Fall is actually one of the most instructive moments in this entire video, because it shows where the real engineering battle is happening right now. It's not about raw compute or elegant design. It's about the grinding, unglamorous work of making complex systems reliable in uncontrolled environments. The companies that close that gap first will define the category. Harvard's rolling contact joints are a reminder that the most consequential breakthroughs don't always trend on social media. Sometimes the thing that quietly changes everything is a new way to design a hinge, one that makes the same motor 3 times more effective. That kind of foundational research has a way of compounding across an entire industry over time. And Westwood's Themis reframes what the actual benchmark for humanoid robots should be. Not can it walk and not can it pick things up, but can it do both simultaneously in an unstructured real-world environment without stopping to think about it. That's the standard humans operate at every single day without a second thought. It's a high bar, but the gap between that bar and what robots can do today is measurably smaller than it was 12 months ago. That's the thing to hold on to. We're not at the end of this story. We're still near the beginning, but if you were watching this space 5 years ago and you're watching it now, the pace of what's changed should genuinely surprise you. Which of these do you think represents the biggest leap? Is it the social realism Moya is chasing, the raw operational endurance of the G1, or is the real breakthrough happening quietly in a Harvard engineering lab most people haven't heard of? Drop it in the comments. I genuinely read every single one, and the debate in there tends to be better than the video. If this was worth your time, subscribe. I cover this space every week. The next one is already in progress, and I'll see you there.